Welcome, everyone. Today, we're diving into modern AI architecture explained. We'll explore the top 10 advanced AI questions you need to know in 2026. We'll cover topics like RAG, AI hallucination, fine-tuning, transformers and attention, and LLM concepts. Our goal is to help you learn, understand, and crack those tough interviews. Stay with us till the end for some real-world explanations. This is AI Interview Questions for Java Developers, Day 2. Let's get started. Let's start by understanding what RAG is. RAG stands for Retrieval-Augmented Generation, and it's an innovative AI architecture that combines two powerful components: information retrieval and generative AI, specifically large language models. The idea here is to produce more accurate and relevant answers by leveraging external data sources. So, how does it work? Imagine a user asks a question. The system first searches through relevant documents or data sources to find the most pertinent information. Then, it sends that data to the language model, which uses it to generate a precise and contextually appropriate answer. For example, if someone asks about Spring Boot security, the system searches through technical documents or manuals, retrieves the key points, and then feeds that to the language model. The result is an accurate, well-informed response. One common challenge with large language models is that they can sometimes give outdated or incorrect answers because they don't always have access to real-time data. That's where RAG really shines. By fetching current or company-specific information before generating responses, it helps ensure the answers are both accurate and up-to-date. So, in essence, RAG enhances AI's ability to deliver reliable, context-aware information by intelligently combining retrieval and generation processes. Let's talk about what AI hallucination actually is. Essentially, it happens when an AI model generates information that sounds correct, but is actually incorrect or even fabricated. It's like the AI is hallucinating details that aren't real. Now, how does this happen? One big reason is a lack of correct or comprehensive data during training. If the data is incomplete or biased, the AI can make mistakes. Overgeneralization is another factor. The AI might apply learned patterns too broadly, leading to inaccuracies. And of course, training limitations, such as insufficient or outdated training, can contribute as well. For example, you might hear an AI say, "Java was created in 2005, which is clearly wrong since Java was actually developed in the 1990s. This kind of error can be problematic in real-world scenarios, especially in critical areas like medicine or law, where incorrect advice can have serious consequences. So, what can we do to mitigate AI hallucinations? One approach is to use Retrieval-Augmented Generation, or RAG, which helps ground the AI responses in actual data. Adding validation layers to check the information before presenting it is also vital. Improving prompts, making sure they are clear and specific, can reduce misunderstandings. All these strategies are part of the broader effort to ensure AI is reliable and trustworthy. Let's start by understanding what fine-tuning actually is. It's a process where we take a pre-trained AI model and train it further on custom data. This helps the model become specialized for specific tasks or information. Think of it as giving the model additional training so it understands the unique details of your business. The process flows from a base model, then we feed it with custom data, and finally, we end up with a fine-tuned model that's tailored to our needs. For example, you might train a model on company documents, FAQs, or support tickets. This way, the AI learns the specific language and information relevant to your organization. Now, why is this important? Well, a generic AI doesn't really understand your company-specific data out of the box. It might be helpful, but it lacks the nuance needed for precise answers or insights. That's where fine-tuning comes in as a solution. By using your internal datasets, we can adapt the AI to better understand and serve your unique context. So, in summary, fine-tuning is a powerful way to customize AI models, making them more accurate and relevant for your specific business needs. Let's start with the definition. Tokenization is the process of breaking down text into smaller units called tokens. These tokens can be words, characters, or subwords, and this step is crucial in preparing text for further processing. For example, take the phrase "Java is powerful." When we tokenize it, it splits into Java is powerful. This simple example shows how tokenization transforms a sentence into manageable parts for a machine to understand. Now, how does this process work? It can be applied at different levels: words, characters, or even subwords. Each approach serves different purposes depending on the complexity of the language or the task at hand. Here's an important real-world problem to keep in mind. Large language models, or LLMs, cannot process raw text directly. They need these smaller, structured units to understand and generate language effectively. And the solution? We convert all the text into tokens before feeding it into the models. This step ensures that the models can interpret and work with the data efficiently, ultimately improving their performance. So, in summary, tokenization is a fundamental step that bridges raw text and machine understanding, making it a key part of the overall language processing workflow. Transformers are deep learning models specifically designed to handle sequential data, which means data where the order matters, like text or time series. They use something called attention mechanisms, which help the model focus on the most relevant parts of the input at each step. This architecture is the backbone of many modern large language models, or LLMs, that we see today. So, how do they work? Well, the process is quite straightforward. You start with the input, pass it through attention layers, and then get the output. These attention layers allow the model to weigh different parts of the input differently, depending on what's most important for generating the output. For example, GPT models, which are some of the most well-known language models, are built using transformer architecture. This enables them to generate coherent and contextually relevant text. Now, a common challenge with traditional models is handling long text dependencies. They often struggle to remember or connect information that appears far apart in the text. That's where transformers shine. Transformers are particularly good at managing long-range relationships within data. They can efficiently process and understand long sequences, making them ideal for complex language tasks. This ability to handle long-range dependencies is one of the reasons why transformers have revolutionized natural language processing. Let's start with the definition. Attention allows the model to focus on the most important words in a sentence, helping it understand context better. Now, how does this actually work? Essentially, the model takes a sentence, assigns important scores to each word, and then focuses on the most relevant ones. For example, if the sentence is "Java developer uses Spring Boot," the model pays more attention to Java and Spring Boot because they carry the key information. This brings us to a common real-world problem. Without attention, models tend to treat all words equally, which can lead to poor understanding, especially when some words are more critical than others. The solution is that attention highlights the important context, allowing the model to prioritize what truly matters in a sentence. So, in essence, the attention mechanism is about guiding the model's focus, making its comprehension more accurate and nuanced. Let's talk about what a context window is. Essentially, it's the maximum amount of text, or tokens, that an AI model can process all at once. Think of it as the model's working memory for a given moment. For example, smaller models might handle around 2,000 tokens, while larger models can manage over 32,000 tokens. This becomes particularly important in real-world situations. When we're having long conversations or working with extensive documents, the model can start to forget earlier parts because it can't hold everything in its context window. This forgetting can affect the quality and coherence of the AI's responses. So, what's the solution? To address this, we can use larger context models that can handle more tokens at once. Another effective approach is to use chunking combined with Retrieval-Augmented Generation, or RAG, which helps the model access relevant information without being overwhelmed. Overall, understanding the size and limitations of the context window is crucial for designing more effective AI systems, especially when dealing with long or complex inputs. Let's talk about temperature in LLMs. Essentially, it controls how random or creative the AI's output will be. When we say temperature, we're referring to a setting that influences the variability of responses. Now, how does it work? Well, a low temperature, like close to 0, makes the output more deterministic. That means it tends to give more precise and consistent answers. On the other hand, a high temperature, closer to 1 or above, increases randomness, encouraging the AI to be more creative and diverse in its responses. For example, if we set the temperature to 0, we get a very precise answer, more straightforward and predictable. But if we bump it up to 1, the response becomes more imaginative and varied. In real-world applications, we've seen that AI can sometimes give inconsistent responses, especially when asked the same question multiple times. That's where temperature settings come into play. To address this, the solution is simple. Use a low temperature when you need accuracy and consistency. But if you're aiming for creativity, like generating ideas or stories, a higher temperature can be very useful. So, controlling temperature is a key tool for balancing precision and creativity in AI outputs, which ties into the overall theme of making AI more adaptable to different needs. Let's start by understanding what zero-shot learning means. Essentially, it's when a model can answer or perform a task without having seen any specific examples beforehand. So, if I ask it to translate hello into Spanish, it can do so even if it hasn't been explicitly trained on that particular translation. It relies on its general understanding and learned concepts. Now, moving to few-shot learning. This approach gives the model just a few examples before asking it to perform the task. For instance, if I show it a few translations like hello to hola, hi to hola, and then ask, good morning to what? The model can use those limited examples to infer the correct answer. This method bridges the gap between no examples and lots of data. In real-world situations, models often struggle with new or unfamiliar tasks. That's where few-shot prompting comes into play. By providing just a few examples, we can guide the model more effectively and improve its performance on new challenges. Overall, understanding these concepts is crucial because they highlight how we can make AI models more adaptable and capable of handling a broader range of tasks with minimal data. This adaptability is a key part of advancing AI towards more flexible, human-like learning. Let's start by understanding what model training really means. Model training is the process of teaching an AI model using data, so it can learn patterns and make predictions. Think of it as teaching a student by giving them examples and letting them learn from those. Now, how does this process actually work? It begins with data, which is fed into an algorithm. The algorithm then uses this data to train the model. Once trained, the model can be used to make predictions on new data. To simplify, it's like passing information through a pipeline. Data goes in, the algorithm processes it, and the trained model produces predictions. Let's consider a practical example, training a model to detect spam emails. You feed it a large set of emails labeled as spam or not spam, and over time, the model learns the patterns that distinguish spam from legitimate messages. But of course, sometimes the model doesn't perform as well as we'd like. It might give poor predictions, which is a common challenge. So what can we do about it? Improving data quality is crucial. More accurate and relevant data helps the model learn better. Increasing the amount of training data also provides more examples for the model to understand. Lastly, tuning hyperparameters. Those are the settings that control how the training process works, can significantly enhance the model's performance. So, in essence, model training is all about teaching AI to understand and predict effectively. And by refining our data and techniques, we can make these models much more accurate and reliable. All right, let's wrap things up with a quick overview of the key concepts we've covered today. First, we looked at RAG architecture, which combines retrieval and generative models to improve accuracy and relevance in AI systems. Then, we discussed AI hallucination, how sometimes models can produce confident but incorrect answers, and the importance of understanding and mitigating this issue. We also touched on fine-tuning, the process of customizing large language models for specific tasks, making them more effective for particular applications. Lastly, we explored the core concepts behind transformers and large language models, which are the foundation of modern AI innovation. Together, these points highlight the overall theme: building smarter, more reliable AI systems by understanding their architecture, limitations, and ways to improve them. Now, for the next step, I invite you to watch the upcoming video on AI tools for developers, where we'll dive into LangChain, AI agents, MCP, and vector search, powerful tools to take your AI projects to the next level. Feel free to check out the playlist and keep learning. And don't forget to like, comment, and subscribe to stay updated. Thanks for joining, and see you in the next session.